Welcome to the course on design of power electronic converters. Today's lecture is going to be on bipolar PWM. Last class we had discussed edge bridge converters and we saw the different possible equivalent circuits and the switching combinations. And there I had mentioned you about pulse width modulations, that there are different types of pulse width modulations for edge bridge converters. And depending on your application you may choose the suitable one. The two most popular ones are bipolar PWM and unipolar PWM. The first one, bipolar PWM, is what we are going to see in this lecture. So, in bipolar PWM what happens is that it uses only the two switching combinations. That means these two devices TA plus and TB minus, the diagonal switch, these two are operated together. They are always turned on and turned off together. And the other two diagonal devices TA minus and TB plus, these are also operated together and always turned on and off together. So, you can consider it like a pair. So, that is like this TA plus and TB minus, these always operated together, and T A minus and T B plus, these two devices are also always operated together. So, only use of diagonal switching combinations. Further, you may recall that what will be the output voltages when your voltage is has to be VO or VDC rather. So, VO, whenever we want it to be equal to VDC, at that time the switch TA plus and TB minus are on, and whenever we want VO to be equal to minus VDC, at that time TA minus and TB plus are turned on. And we had also seen before that what will be the corresponding DC bus current. IDC is going to be plus IO whenever TA plus TB minus are on, and it is going to be minus IO whenever TA minus and TB plus are on. Okay, and depending on the direction of the current, either the switch will be conducting, that means the MOSFET will be conducting, or the diode will be conducting. So, these things we have seen before. So, now let us look into the waveforms. So, this is the carrier waveform which is shown here, which is triangular carrier is chosen, and this has the switching frequency Fs. Okay. So, the time period, one time period that you see here, this is equal to Ts, the switching time period. Then this is the reference, this one is your VO ref, the output voltage reference waveform with which we do the comparison. And then on comparison, what we observe here is that the logic that is followed is whenever VO ref is greater than V carrier, at that time TA plus and TB minus are turned on. And whenever the opposite is happening, that means V carrier is greater than VO ref, then the other two diagonal devices TB plus and TA minus are turned on. Okay. So, we can do these comparisons like this at every point, and then accordingly here the output voltage, wherever TA plus TB minus are on, at that place the output voltage is going to be equal to plus VDC. Otherwise, the output voltage will be equal to minus VDC. So, the output voltage then switches between plus VDC and minus VDC continuously. And what will be the leg voltages? So, leg voltage will be what, whenever the upper switch is on, at that time it is VDC, otherwise it is 0. So, the leg A voltage VAN, here TA plus is on, so it is equal to plus VDC, and otherwise this is Ta minus is on, so it will be equal to 0, and so on. Similarly, for the leg voltage VBN also we see the same thing. Here TB plus is on, upper switch of leg B is on, so this is VDC, and here TB minus is on, and so the leg voltage is equal to 0, and this continues. Okay. Then the load current. Now load current for the waveforms that is shown here, it is assumed that the load current is all throughout positive. Okay, it is not going negative. Now it depends on the load, do not think that that is the case always, it may become positive, negative, it depends on the load and also on the output voltage. So then what will happen whenever the voltage applied is plus VDC at the output, at that time the load current will increase. Okay, and then because most of the time the load is going to be inductive in nature. So, when you apply a positive voltage across it, the current will increase, and then when we apply a 0 voltage or a negative voltage, then the current will reduce, and so that is what is happening over here when this voltage is, output voltage is minus VDC, and this is continuing. Now, what about your IDC, the DC bus current? So, DC bus current, here we see that in this part which are the devices conducting, TA plus and TB minus. Okay. At that time what will happen? Your current will be equal to IDC. IDC will be equal to IO, and whenever the other two diagonal switches are on, IDC will be equal to minus of IO, and that is what we observe here, that whenever TAB plus and TA minus are on, so this part is opposite of this part. Whenever over here this is when TB plus and TA minus are on. Okay. Then your this device voltages. Now blocking voltage will be VDC, VTA plus TB minus whenever they are not conducting, this will be equal to VDC, else whenever they are conducting, for ideal case it will be 0. And similarly you can draw the other waveforms also, VTA minus and VTB plus. Okay. Whenever they are conducting, 0, not conducting, blocking voltage is VDC. And the current that is carried by the devices. Now here what we have assumed, the current direction is always positive. So when the current direction is all throughout positive, what will happen whenever these two switches are turned on, the first two diagonal switches, it is TA plus and TB minus which are going to conduct, and whenever the opposite is happening, so at that time the current direction is like this. So it flows through the diodes, comes through here, and it flows through the diode here as well. Okay. So DA minus and DB plus, the two diodes are going to conduct, and that is what we see here. ITA plus and ITB minus carries the current IO whenever they are on, and else whenever these other two diagonal devices are on, it is the two diodes which are carrying the current. Now this is the waveforms that are shown here, they are assuming the VO ref is a DC reference. Now this edge bridge is also used for your single phase DC to AC conversion. So there the reference can be sinusoidal. So how the waveforms are going to be then? So this is your VO ref which is sinusoidal here, you can see there, and this reference, this is a triangular carrier which let us say goes from 0 to 1. So, obviously this also can have maximum value as equal to 1 and not more than that. If it becomes more than that, so then it will be greater than the carrier waveform, and then the pulses will start getting missed out. Okay. And then this is the VO average. So, what this pulses that we are seeing is what we get by doing the comparison. So, when we do these comparisons here, so whenever this reference is greater than the carrier, your output is going to be here equal to plus VDC, else this is going to be equal to minus VDC. So, this is what is your 0 over here. So, this is your 0, it goes from plus VDC to minus VDC, and this waveform is actually the VO waveform, the actual output voltage which you will see on the oscilloscope, the instantaneous voltage waveform. And if we take the average of that waveform, if we do the average of it, so that is this VO bar. For every Ts time period, every switching time period, if you take the average of VO, then what you will be getting is this VO bar, which is this sinusoid which you are getting, and which has to resemble the reference waveform to begin with. This average is also, you can say, is the fundamental component of this switched voltage waveform. Now, next let us see how to obtain the reference waveform. How do you obtain the equation for it? So, for that let us consider only one switching time period Ts. So, let us say this is your VO waveform for one switching time period Ts, and this part is when the first two diagonal switches are on, so we call it as DTS, and this other is your 1 minus DTS. And this waveform will have an average, and that is that VO bar that we are talking about, and this varies from plus VDC to minus VDC. So, we can write this VO bar as equal to VDC into DTS plus minus VDC into 1 minus DTS by Ts. So, then further what you get from this is VDC into 2D minus 1 is what your VO bar is equal to, from which you can write D as equal to VO bar by 2 VDC plus half. So, using this equation you can obtain the duty ratio. Now, if VO bar is something varying, is what our target voltage, target output voltage is a sinusoidal voltage. Let us say this is VO hat sine of omega 1 t. Now, I am using this omega 1 to denote that this is the fundamental. So, in that case your duty ratios itself, that modulating waveform is your VO ref, what we can call it as. This is equal to your VO hat sine of omega 1 t by 2 VDC plus half. So, this is the modulating waveform, equation for the modulating waveform which you can use to compare with the triangular carrier and generate the gate pulses for the bipolar PWM. There is another term corresponding to pulse width modulation which is used in power electronic converters, which is called as the modulation index. Now, this modulation index, it is denoted as MA many times, is defined as VO hat by VDC. Now, I am defining it as VO hat, the peak of the output voltage by VDC. Peak of the output voltage means the averaged waveform, VO bar of that's the peak of that. Sometimes in books people also write the RMS value of it. So, know that your value of modulation index will change accordingly. So, you can use either definition, but you just have to be aware which definition you are using, because your modulation index value will change accordingly. So, now what happens is that if this is your triangular carrier waveform and then you have this reference, now your this carrier varies from 0 to 1, let us say. Now, the VO ref that we are using, it can have a maximum value as equal to 1, otherwise it will start crossing these carrier peaks. Okay, and so then what will happen is that the comparison will not happen. Some pulses will start to miss out, like for example, if the reference waveform becomes like this. So, here till here you will actually get no pulse. So, then that means we are losing over the control, the desired average waveform that we were supposed to get, which we are targeting, that is not going to come by the PWM method, and it will have more harmonics into it, lower order harmonics may start coming as well. So, this is mostly avoided, but although there may be situations where this rule may be violated, that we would like to keep this reference waveform below 1. So, then what that is called as over modulation. So, that is also done, but for our purpose we would not like to violate it. Let us say we want to keep it below this, the reference should be below the carrier waveform's maximum. So, accordingly there is a maximum value for this modulation index, which this modulation index can take for a particular method of PWM. So, then if we want to write that, if we want to find out that for bipolar PWM what that maximum modulation index is going to be. So, your VO ref that means can be maximum equal to 1. And so, your VO hat by 2 VDC plus half can be maximum equal to 1 according to the equation that we found out just now. So, if you solve it, what you get is that VO hat can be equal to VDC. So, that means your maximum modulation index can be equal to 1 in case of bipolar PWM. So, what is the use of this maximum modulation index? This gives us an indication of what is the minimum VDC that you require for your converter. Usually when you are designing a converter, then you know what is your output, what is the targeted output. Then if you have the targeted output, then you have to find out how much is the DC bus voltage that needs to be created. So, using the maximum modulation index for the particular PWM you are using, you will be knowing that this is the minimum DC bus voltage that is required. Okay, so, maximum modulation index indicates minimum VDC needed to obtain VO hat. Now, let us find out an expression for capacitor current. This capacitor current also plays a very important role in the choice of capacitor. And here to do this we will ignore the switching frequency component. We will use this IDC bar, because your DC bus current is IDC, which is the actual current, but we will be ignoring the switching frequency components for now, and that we will be denoting as IDC bar. So, everything taking as the averaged expression. So, VO bar is VO hat sine of omega 1 t, and IO bar, this is also the average of the output current, the load current over one switching time period. So, IO hat sine of omega 1 t minus, let us say, phi 1, there is a lag in it, and which is phi 1. So, if we assume everything to be ideal and lossless, we can write VDC into IDC bar as equal to VO bar into IO bar. That is, the DC power is equal to AC output power. So, then you substitute it VO hat sine of omega 1 t into IO hat sine of omega 1 t minus of phi 1. If you solve it, you have to do little trigonometry here. If you solve that, what you will be getting is this VO hat IO hat by 2 VDC cos of phi 1 minus VO hat IO hat by 2 VDC cos of 2 omega 1 t minus of phi 1. Now, what you observe here is that this component is not varying, it is a DC value. So, this is your DC component IDC of the capacitor current. Usually what we will expect is that it is a DC bus current, means it should be a flat DC, but we have seen that it is a flat DC is not what flows through the DC bus, it is a ripple, it has got a switching frequency ripple, which we have ignored. So, then definitely it should be only the DC component which should be there. So, that of course we are seeing, but what we see is that there is something else to it, and this is varying with a frequency twice the fundamental. So, this is the second harmonic of omega 1. Okay, so, second harmonic component is also present in case of edge bridge converter when we use this bipolar PWM, and that is a disadvantage, because then second harmonic is a much lower frequency harmonic. Let us say if you have a 50 hertz output, then you in the capacitor current there is a 100 hertz component. So, you have to choose a capacitor large enough which can withstand that 100 hertz component of current in the DC bus and still maintain the DC bus voltage. So, let us look into the current waveforms. So, this is the output voltage waveform, instantaneous output voltage waveform. This is your VO, which varies from plus VDC to minus VDC, and this is the 0 of it. Okay, instantaneous output voltage waveform, and this is the VO bar, the average of it, what we saw over switching time periods. If we average the instantaneous output voltage waveform, we will be getting that VO bar. Then what happens further is that if we draw the load current waveform, then if it is a sinusoidal waveform, the load current will be how it is going to appear, since it is assuming an inductive load. So, whenever the voltage is positive, so here the voltage is positive, it is plus VDC, what will happen? The current will increase, and then whenever the voltage is minus VDC, the current will decrease. and this nature of the current increasing decreasing, it continues and it follows a kind of a sinusoidal nature. Okay. So, then your this current, this is your actual IO current which you will be seeing on the oscilloscope, and if you again take the average of it, so that is the average current, this is the average current, the black one is the average current IO bar which we just used for calculation just now, IO bar, and IDC waveform. So, this is the IDC waveform. You can see here that whenever your this part, let us say whenever the first two diagonal switches are on, at that time this is equal to IO. So, here this is equal to IO. So, this part it is equal to plus IO, and this part you can see that it is equal to minus IO here, and so forth, it continues like this. So, using this waveform you can find out this IDC waveform also, alright. And what we see is that it's a very switched current waveform. So, it has got several components in it. One component is your this DC that will be there, which is your IDC, and then it will have also the second harmonic component. So, that will be your IDC 2, let us call it as, and of course, the switching frequency component will be there, and finally, this is your actual IDC waveform that we see, that you are going to see on the oscilloscope. So, the key points of this lecture are that when you choose a modulation strategy, you have to analyze that modulation strategy. Different modulation strategies are there. You can pick one for your converter, you can analyze different waveforms for that modulation strategy. And you have to find out the modulating waveform, because when you are going to design it, you have a particular output, you need that output. So, you have to get the modulating waveform which can generate that particular output. So, those equations are required. And then you also find out the maximum modulation index, that will give you an indication of the minimum DC bus voltage that is required. And you should also observe the capacitor current ripples, or you can find it out if equations are available for that, or you can simulate and you can observe the capacitor current waveforms. Then that will give you an idea that how big capacitance you need to maintain the DC bus voltage. Thank you.